Hello, my name is Bum-Young Kim from Naver Cloud. Thank you for your interest in our paper. Let me introduce my paper, The Devil is in the Points Weakly Semi-Supervised Instance Segmentation, via Point-Guided Mask Representation. Let's begin. First, we will give you a short 1-minute preview. In this paper, we propose a new training scheme, named Weakly Semi-Supervised Instance Segmentation, with point labels. Here, we use a lot of point labels and a few fully labeled labels for budget-efficient and high-performance instance segmentation. Our key insight is that point labels can be leveraged as a key source for successful semi-supervised instance segmentation. Consequently, we achieve budget-efficient and high-performance instance segmentation results. That was our preview. From now on, we will provide more details of our work. The first is the introduction section. First, we explain the motivation for this work. Most existing instance segmentation methods adopt a two-step inference process. The first is generating instance proposals in the proposal branch. The second is producing instance masks for each instance proposal in the mask branch. Here, we found that the matter is the proposal in instance segmentation. As shown in the Bellow figure, missing proposal causes false negative prediction, even though the model was able to represent the instance mask in the mask branch when given the correct proposal. Also, noise proposal leads to false positive prediction. This finding is easily discovered by adjusting the threshold in the proposal branch. When the threshold in the proposal branch is low, we can get more true positives, but many false positives follow. In contrast, when the threshold is high, we can reduce the number of false positives, but lose many true positives. Such trade-off is a main challenge in semi-supervised instance segmentation. Then we introduce our proposed method. In this paper, we introduce a new learning scheme, named Weakly Semi-Supervised Instance Segmentation, with point labels. In this setting, we consider we have a lot of point labeled data, and a few fully labeled data. Then, this is an overview of our paper. First, we train the model using only strong labels to make the model can represent instance masks. Then, using the rest point label data, we generate pseudo-instance masks via point prompting. Both pseudo-labels and strong labels are employed to train a baseline instance segmentation network. By filtering the instance proposals via point prompting, we can obtain accurate proposals, resulting in high-quality pseudo-instance masks. Then, we will explain the detailed components of our proposed method. For better exploiting point labels, we propose adaptive pyramid level selection. Under the FPN architecture, each pyramid level recognizes instances of particular sizes. However, point labels do not have instance size information, and extracting instance masks from unfit levels often causes inaccurate prediction, as shown in the right figure. Therefore, we estimate which level is the best fit based on the reliability of the network, and adaptively produce an instance mask at the selected pyramid level, as shown in the left figure. Due to this strategy, we can generate more accurate pseudo-instance masks. When given a sufficient amount of fully labeled data, the network can generate quite reasonable pseudo-labels. However, when given an insufficient amount of fully labeled data, the network often fails to sufficiently represent the instance mask in the mask branch. To address this limitation, we propose mask refinement network. The below figure illustrates the overall training pipeline for Mask Refine Net. The Mask Refine Net refines rough mask output, from the teacher network based on 3 input sources, including input image, rough mask, and point information. We loosely crop each instance region in the 3 input sources and resize them to 256 by 256 and concatenate them to be an input tensor. In the pseudo-label generation stage, the mask RefineNet takes the mask output from the teacher network and refines it. Refined pseudo-labels and strong labels are used to train the student network. As shown in the below results, some erroneously localized predictions in the rough mask can be refined by the mask RefineNet. Next is the experiments section. We adopt to benchmarks, COCO 2017 and BDD 100K datasets. We randomly sample subsets. For instance, COCO 5% denotes containing 5% of strong labels and the rest 95% of weak labels. We estimate the labeling budget on COCO for each labeling source. Note that the labeling cost of point labels is quite budget-friendly. As shown in the left figure, the proposed method is compared with training using only fully labeled data, and training with fully labeled data and unlabeled data. Consequently, ours can achieve remarkable performances on all COCO subsets. Especially, ours show much a higher performance on smaller subsets, such as COCO 1% and 5%. In addition, our method with COCO 50% shows a highly competitive result, compared to COCO 100%. Also, as shown in the right figure, we compare other methods based on the labeling budget and achieve the best accuracy budget result. This figure is our qualitative results. Even if we use only 5% of fully labeled data, we can achieve a quite competitive result. Then this is our last section, the conclusion. We show that point labels can be leveraged as effective weak supervision for budget-efficient and high-performance instance segmentation. Based on this observation, we establish a new training protocol named Weakly Semi-Supervised Instance Segmentation with point labels. For better exploiting point labels, we propose the adaptive pyramid level selection and mask RefineNet. The proposed method can achieve competitive performance to those of the fully supervised models, while significantly outperforming the semi-supervised methods. This is our last slide. Thank you for listening to our presentation.